Starting with the fundamental theorem of algebra, every polynomial has at least one zero in the complex number system. Complex number system includes imaginary numbers, but also remember that a complex number could be just a real number. Real numbers are included within the complex number system. So at any rate, basically, we're adding i's now. And how do you know the total number of zeros? You should remember this from before, like how many solutions does an equation have? Remember that solutions, zeros, roots, they're all the same thing. So how do I know the total number of zeros that I have? It is based on the highest power of the variable. So it's based on the highest power of the variable, which, if you remember from Algebra 2, that just means the degree of the polynomial. So if we start with the examples below, you see that we have this polynomial, x plus 7. The power is 1. So how many zeros could I have? The fundamental theorem of algebra tells me that I have 1. So I have 1, 0. And in this case, it would have to be a real zero meaning it actually crosses the x-axis, because this is a line. Now, you might be thinking, well, not all lines cross the x-axis. Well, actually, they do, all except horizontal lines. And that's the special case. This would be a horizontal line, right? I'm going off on a side here for people who want to understand this. This would be a horizontal line. A horizontal line doesn't cross the x-axis because there is no x here, right? So it would have 0 x-intercepts. But that's a tangent. We are looking at the fact that this is the first power, so it's going to have 1, 0. The 0 is going to be real. How do we find zeros? We set the polynomial equal to 0, and we get x equals -7. So that's the first degree polynomial. A second degree polynomial, or a quadratic, would have 2 zeros. So this one, because it's the highest power, it has 2 zeros, but they might not be real. But they might not be real zeros, meaning they wouldn't cross the x-axis. So meaning they may not cross the x-axis because they could be imaginary. And you may or may not remember that imaginary numbers, just like irrational numbers, things with square roots and i's, always come in pairs. So if I say there are 2 zeros, how many real could there be? There could be 2 or 0 real zeros, because they both could be imaginary. And we just solve this by setting x squared minus 3x minus 4 equal to 0. And then we factor x minus 4, x plus 1. So our zeros are x equals 4 and x equals -1. And they are both real. So 2 real zeros there. Now when I go up to cubed, I definitely have 3 zeros. But, right, 2 of them could be imaginary. Remember, they come in pairs, so it's 2 of them that could be imaginary. Therefore, 3 or 1 are real zeros. So let's see what they are. If you go over here, again, finding zeros, you set it, the polynomial equal to 0. Factor out an x, you have x squared plus 4 equals 0. Now you know that x equals 0 is one of the zeros, but here, this doesn't factor. And if you tried to solve that, so I'm going to come over on this side over here and solve it, x squared plus 4 equals 0. You get x squared equals -4. And then when you take the square root of both sides, hopefully you remember that you get positive and negative 2i, because the negative under the radical just means it comes out as an I. So my other zeros over here are positive and negative 2i. And if you notice, I have one real zero, and I said I would have either 3 or 1. I have one real zero and 2 imaginary. So this graph is only going to cross the x-axis once. Moving on to something to the 4th power. Well, keeping with what we've been saying here, so if it's to the 4th power, that means I have 4 zeros, but 4 or 2 or 0 of them are real. And then we'd go ahead and try to set this equal to 0, x to the 4th plus x cubed plus 2x squared minus 12x plus 8 equals 0. And we have no idea how to do that because we have not yet learned how to factor something like this when I don't give you a hint on how to start. But you are going to learn that. When I say I want to factor it into linear factors, we did that above. It was just x minus 4 and x plus 1. And then what did I do? For the zeros were just 4 and negative 1. And then back here, when I had something that was cubed and it was easy to factor, same thing. I factored out an x and I got x squared plus 4. But then remember, here I said linear factors. So that means that I have to factor this into x plus 2i and x minus 2i. So that again is above, so that shouldn't really be a big deal. And then over here, the zeros are 0 and positive negative 2i. Notice that they are all zeros, but they are not all real zeros. So if I had asked you for just the real zeros, you would have told me just this, but I asked for all the zeros. So when you can't factor, then, and if it's second degree, it has to be second degree. This, what I'm about to say, won't work for cubes, because what do you do if you have a second degree polynomial and you can't factor? You just use the quadratic formula, right? So the quadratic formula, or you could polysimult. Now, the only issue with polysimulting is that it's going to give you a decimal answer. So when I ask you for linear factors down here, you are not going to be able to write the decimal. You're going to have to write it the way it would come out in the quadratic formula. So remember, when you do the quadratic formula, you will always end up with something like, I don't know, I'm making this up, 3 minus the square root of 2 over 2. You would have to write it x minus 3 minus the square root of 2 over 2. And then remember, the other factor would be x minus 3 plus root 2 over 3. And again, if you weren't listening, this is just to show you what it would look like, because I'd have to use the quadratic formula to get these numbers. I cannot use the decimals from polysimult. So you might be saying, well, why'd you teach us polysimult if we can't use it? Well, you can use it to find the zeros and to help you graph, but when I ask you to factor linearly, you're going to have to make sure you get these answers. So let's go ahead and actually do this problem now. You may or may not realize that it doesn't factor. It looks very similar to the one we did, but it does not factor. So the quadratic formula, I'm going to go ahead and do it. I'm going to plug it into polysimult. And then I'm going to come back with the answers. So if you used the quadratic formula, this is how you would get the answer for the polysimult answers. But I asked you to put this into linear factors, so you have to do it using what you got from the quadratic formula. So it would look like this: x minus and then it was 3 plus root 5 over 2, and x minus 3 minus root 5 over 2. So that is factored into linear factors. And moving on. If it's a polynomial of degree higher than 2, I use something called the rational zero test to start trying to factor it. And I say higher power than 2 because we should already know, but we just looked at the fact that if I had something like y equals x squared plus 2x plus 1, what I would do is try to factor it, and if I couldn't factor it, then I'd use the quadratic formula. So there's always something we can do. Now, sometimes when you get up to something cubed, like let's say this was x cubed, x squared, and x, we could actually still factor that because we know all we'd have to do is factor out an x. But as we get higher, that might not always be the case. I might give you something like y equals x cubed plus x squared plus 1. And that we have no way of factoring. So we're going to use what's called the rational zero test to help us get started. And the rational zero test says that for any polynomial with integer coefficients, if a rational zero exists, rational meaning real, and also rational meaning it won't have a square root. Okay, so this is again the rational zero, meaning there's not going to be any square roots. So if it has a rational zero, it'll be of the form p over q, where p represents the factors of the constant at the end, and q represents the factors of the leading coefficient. And I'm sure by now you know that the leading coefficient isn't always necessarily going to be first, because they like to do fancy things like this on you and put y equals 2x squared plus 5x cubed minus 9. And really our leading coefficient is this one because it goes with the highest power is 3. They just decided to be cute and put it in the wrong order. So anyway, what we do is then write them as at p over q. And what does that represent? That represents all possible rational zeros. So all possible rational zeros. Side note, not all zeros in the list of possible will work. So I'm just writing a list of possible, but they don't always all work. In fact, sometimes none of them will work, and then in that case the zeros are either irrational or imaginary. I know it's a lot of words: possible, rational, real, irrational, imaginary. So you've really got to know what rational means, what a zero is, what irrational means, what imaginary is. But let's practice what I just taught you here. So for this problem, I'm being asked to find all possible rational zeros. So I know I'm going to be doing this p over q thing. So what is my p? My p is the number at the end. It's the constant. So it's negative 10. And what are my factors of p? Well, 1 times 10 is 10, and 2 times 5 is 10. So I've got 1, 2, 5, and 10, but also plus minus for each of them, because negative 1 times positive 10 is negative 10, and negative 2, I don't think I need to explain that. You know what I mean. And now we look at q. Q is the leading coefficient, and the leading coefficient is 4, and my factors of that are 1 and 4, or 2 and 2, right? So I've got 1, 2, and 4, but again, plus and minus, because negative 1 times negative 4 equals 4, right? Just as 1 and 4 equals 4, and 2 times 2 equals 4, and negative 2 times negative 2 equals 4. So the positives and negatives always go with these. But I'm not done. What did they say I need to do now? I need to put all my p's and q's over top of each other. So I start with my p's. So my p's are positive negative 1, positive negative 2, positive negative 5, positive negative 10. And it says I'm supposed to put it over all of the q's. Well, where are my q's? Well, I guess I could start with 1. I could put every single one of these over 1, but that doesn't change anything at all, right? So I'm just not even going to bother putting them all over 1 because they would be exactly as they are now. But I will put for the next set, this time, again, I still have positive negative 1, 2, 5, and 10, but now I'm going to put it over this factor. So it's going to be over 2, and you don't really need to write the positive negative again. It's already written up here, so you're just going to put each thing over 2. Well, you'll notice 2 over 2 is just 1, and we already have that. So 2 over 2 is just 1, which we already have, so we can cross this one out. That's a repeat. And also then this one, positive negative 10 over 2 is just 5, so we can cross that one out. But we've got to keep going because we've got another factor here. So we take all our factors of p, so positive negative 1, positive negative 2, positive negative 5, positive negative 10, and now we put everything over 4. And now again, we're going to have some repeats here. So 2/4 reduces to 1/2, which we already have right there. So we can get rid of 2/4. And then 10/4 reduces to 5 over 2, which we already have over here. So we can get rid of that one. So our list of all possible rational zeros is, I'm just going to circle them, positive negative 1, positive negative 2, positive negative 5, positive negative 10, positive negative 1/2, positive negative 5 over 2, positive negative 1/4, positive negative 5/4. So any one of those could be a rational zero. Unfortunately, none of them might work, but you always have to start by listing the ones that could work. So you guys do the next two and then come back and check. So there's your answers, and if you want to just pause it so you can check it against yours, that's great. And I'm going to move on. As you may have noticed, there's so many ways I could ask the various questions. So I listed all the things I could be asking you here. I could say, how many possible rational zeros are there? List all possible rational zeros. Find all rational zeros. Find all real zeros. Find all the zeros. Factor completely into linear factors or graph. No matter which one of these 7 questions I ask, you always start by listing all possible rational zeros. So let's do this example. Factor completely into linear factors, then graph. So I have no idea how to factor this just by looking at it. We don't have any methods, so we might as well start with what are our possibles. So remember that's P over Q, and it's always positive, negative. And this is our P, and this is our Q. Luckily, we only have 1 here, so that means it's just really P, the factors of P. So my possibles are positive, negative 1, positive, negative 2, positive, negative 4, positive, negative 8. Once I have the list of all possible, then I have to test the possible zeros to see which ones work. How do I test? Well, remember there were 2 ways to test. I could just do the synthetic division and try it. So I could say, okay, I'm going to put 1 in here, and that would be 1, 1, 2. Oh, wait, there's a 0 in there somewhere, right? Because there's no x to the 4th term, so this is 0. And then 1, 2, negative 12, 8. And then that would be 1, 1, 1, 1, 2, 2, 4, 4, negative 8, negative 8, 0. Oh, yay, that one worked. So we just found out that 1 is a 0. And that's great, because now what does that mean? That means that I have x minus 1 is a factor. So that would be x minus 1 times x to the 4th plus x cubed plus 2x squared plus 4x minus 8. So I've actually started factoring this, and this is what it looks like. But we just happened to get lucky by one being one that worked, and I did that obviously on purpose so that we could get lucky right away. But if we don't find one right away, or even if we do, because we still got more to find, we go to the next number. So we tried 1. Now we would try -1. The other way to see if something works, if you don't want to do the synthetic division, is you can just plug it in. Remember, f of -1. So if I plug it in, I get -1 to the 5th plus -1 cubed plus 2 times -1 squared minus 12 times -1 plus 8. So I have -1 plus -1 plus 2 plus 12 plus 8. And when I add all that up, I do not get 0. So -1 is not a 0. So I would just keep testing right now. Whoops. Right now it's factored into this, but I need it into linear factors so that I can graph it. So what do? Well, from this right here, I have to factor this. What are my possible factors? Your possible factors are still the same ones as they were originally. So positive, -1, 2, 4, and 8. Those never change. Your possibles never change. We already tested -1 and saw that it didn't work. We tested 1 and we saw that it worked. 1 could work again because it could be a double root, but chances are that it will not. So let's just move on and try 2. And we know that there are 2 ways to check. I could either do 2 with synthetic division, or I could plug in and find f of 2. So this would be, now remember, I'm looking at this for my coefficients. So this would be, let's see, it would be 1, 1, 2, 4, -8. And that would be 1, 2, 3, 6, 8, 16, 20. Yeah, that doesn't work. So we know because we didn't get 0 here, we're not going to get 0, right? I didn't even finish doing the math, but we know we're not going to get 0. So we know that 2 is not a solution, which we could have also figured out had we just plugged in f of 2. Which would be -2. And we're just going to try it in the synthetic division using the 1, 1, 2, 4, -8 like last time. And then we have 1, -2, -1, 2, 4, -8, -4, 8, 0. So yay, it worked. And the nice thing about testing it using synthetic division is that if it does work, then you've already started factoring, right? So now we know that this is a 0, which means that x plus 2 is a factor. And then from up here, we had x minus 1 was a factor. And then what's left is what's right here. So for my powers of x, x goes to what power? Well, I look up here, the highest power was 4. So this one is going to be 3, and then x squared, and x, and not have one. So what do I put then in here? Whoops, I didn't mean to make it look like that. Is x cubed minus x squared plus 4x minus 4. So now I've factored even more, and I'd have to keep going. So you might be looking at this and thinking, oh man, this is cubed. I don't know a method to factor it. So now I'm going to have to test another of these numbers, these possibles from up here. But that is not the case because this actually factors by grouping. So if I group the first two, I can factor out an x squared, and I get x minus 1. And if I factor out a 4, I get x minus 1. So now this whole thing factored into x squared plus 4 and x minus 1. And then don't forget, now they said at the very beginning, all the way back, I think we wanted linear factors. Well, that's actually one of the questions we could be asked. This is not a linear factor because of the squared there. So how would I solve this one? Well, this one factors into x plus 2i and x minus 2i. So anyway, I also have the x plus 2, and then I have the x minus 1. So now my polynomial is factored completely. Side note, not all zeros in the list of possible. So our zeros are, again, -2, 1, which is over here as well, so it was a double root. So let's put those on there. We've got -2, which is right here, and then we've got 1, which is a double root. And what do we look at to see where we start? Well, we look at the very beginning. I just rewrote the original here so that you could see the leading coefficient. So we're looking at this, and it is positive and odd. So positive and odd is up on this side, down on this side. So in my graph, I'm going to go up on this side, down on this side. And then we know that it just goes through -2. And then 1 was a double root, so it's a bounce. So I'm going to come up, I'm going to go up through, and then I'm going to go to 1, and it's going to bounce because it was a double root. And that is all I'm going to do on this video, because I am sure you are sick of listening to me, and that was a very long problem.